I work for Parity Technologies. So some of you might know about Parity already. If not, I'll give a brief description of what we do, which is what we would call core technology. So things like Ethereum clients, but also just lower level applications or infrastructure projects that other apps can leverage. So today I'm going to be talking a bit about our Ethereum client, specifically the Light client framework. So I would break this down first into defining, So I would put this down first to defining different classifications of Ethereum clients. So first we have our basic full nodes. So what full nodes do is they download every single header, every single block, they execute them all in order, starting from the genesis, make sure that not only is the consensus done correctly, but also all the transactions execute correctly and all the data checks out. So this is actually a fairly heavy operation. And if any of you have tried to run a full node recently, you might notice that this is using a lot of storage on your computer, a lot of CPU, a lot of memory. So then the next level down would be light clients. So that's primarily what I'm going to talk about today. So what a light client does is it just checks the block headers. So it starts at the genesis, say, and downloads all the headers starting from there, and it verifies that consensus has been done correctly. But it doesn't execute the transactions in the block, so it does lose a little bit of information along the way and perhaps a little bit of security. And the last classification of Ethereum clients is one that I would call thin clients. So a thin client is basically just a wrapper around a remote node. So you have a website that knows a node somewhere else, and it just asks it for data unproven about the state of the Ethereum chain. So if we talk about the security guarantees of a light client, it checks the validity of headers, so it checks the proof of work, or perhaps once Ethereum moves to proof of stake, it would check a signature by some authority or validator. But it doesn't check the validity of state transitions, that transactions have been executed correctly, or that block rewards have been given out. So to think a bit what kind of attacks this leaves us open to, we have to think about the behaviors of other nodes on the system. So first of all, we have an honest majority assumption with the miners. So if you take this assumption that the majority of miners aren't going to be producing invalid blocks, then unless you have some other miner directly targeting you and sending you invalid blocks, you won't be able to see invalid blocks that have those invalid state transitions, which you wouldn't be able to detect as a light client. So that leaves us open to a very targeted sort of attack where you have an attacker who knows that you're running a light client, and for whatever reason it's valuable to him to take up all your peer slots and start sending you invalid blocks to try and fool you into sending a transaction that you don't want to. Because another thing that can't happen is for him to trick you into thinking that the sending, no. So well, actually that's not correct. So he can fool you into thinking that the current state is different, and he can send you proofs on that. But if you do go back and check that the transitions have been done correctly, which you would if you have a high value application that's running, you cannot be fooled. So we have a goal when we're designing our network protocol. So the first goal is to minimize the round trips and bandwidth. So we have a few core pieces, one of which is back referencing, the second of which is to check state proofs, and the third of which is a pub-sub network protocol. And the goals are really to leverage that security assumption of the Ethereum chain as highly as possible. So we've checked the consensus, and that means that we trust some block header hash. This block header contains a state tree root, and we want to say that any state data that we read from the chain can be provably connected to this state tree root. So we design all of our requests around this provable data. And the last thing is we want to think about avoiding denial of service or just spam of protocol servers. So when you're a light client, you have to ask your peers, prove this data exists in the state right now. And if we don't have some kind of layer to prevent people from making tons and tons of requests, it could be that the protocol servers are overwhelmed by that. So we want to think a bit further in the future about things like micropayments, and we would leverage technology like state channels, for example, to make those micropayments very small, but actually provide an economic incentive to serve that data. So to speak about back referencing, this is, I think, a really critical part of that light client protocol, because as you recall, we don't have the state. So we might want to fetch a block header, and then from that block header, get a state proof of an account's existence. And then we have, from that account structure, we can get a reference to another Merkle tree, which stores the storage for that contract. So we have 3 pieces of things that we want to fetch. We want to fetch the header, then the account, and then some storage. So that actually logically requires 3 requests. But imagine if you have a 100 millisecond latency with your peer. If you go there and back and there and back and there and back, that's 600 milliseconds of latency. And that's actually a very long time to make a simple contract call to your peer. So we have this idea that we have heterogeneous requests embedded in a single packet where the later requests in the packet can reference data that's output by the prior. So in this way, we can do these 3 requests, or basically any other kinds of requests, for example, even smart contract executions. They're very composable. We can do all of that in a single round trip, and it's still provably secure, but you get a much lower latency, and that's a better user experience. So to speak a bit more about these state proofs, we have a state tree here, right? So that root of that tree, the very top node, is embedded into the block header through a cryptographic reference. And when we execute a Turing-complete smart contract, it's actually unpredictable which pieces of data we want to fetch from that state tree, because it requires execution of arbitrary code. So if you are using a light client and you want to, say, do an Ethereum name service lookup, like this might require fetching all kinds of different pieces of data from the network. And if you were just executing it locally, and every time you need a piece of data to go to a peer and ask, give me this account, give me this storage, it would actually take a really long time. So the second aspect of our minimizing round trips goal is to do entire transaction state proofs, so that when you want to see what the result of a call would be prospectively, you can just ask a peer, prove this call to me, and not just do it piecewise, which is too inefficient. And the last thing is we introduce a model of something called request credits. So these servers give the light client peers little credits that can be used to make requests. So credits might recharge slowly over time. This is how it works now. So every time you want to make a request for, say, a header or a piece of the state, you use a little bit of these credits. And different servers will have different costs. It'll be based on, their empirical measurements of how long it takes to serve a specific request. So that makes it adaptive to improvements in storage hardware or growth of the Ethereum state, etc. So this is actually a pretty generic scheme that can be used to leverage micropayments as well. So instead of having them recharge over time, when you pay a server, they give you some request credits. So the last thing we want to think about is this concept of a publish-subscribe system. So our full node peers, as a light client, know a lot better when something has changed in a contract than we do, because we just don't have that state, and it's fairly bandwidth intensive to download the updated state every block. So if we can introduce a publish-subscribe system, our peers can push that data to us as it's updated. But the hard part is there's no real way to check if a full node peer has just skipped sending us something that has changed. But what we can do is also farm out requests to multiple peers, and if they differ, perhaps there can be some kind of on-chain dispute resolution where a bond gets slashed. But this is definitely an area for open research. So another optimization that we have in the light client is this idea that we shouldn't have to store all the block headers from the genesis up until now. It's something like 5 million or so now. It's just going to keep growing. So that's a lot of block headers to keep around. So we have an idea that we can instead store a mapping from block number to the hash of that header and the total difficulty of that header in the form of a Merkle tree. But we actually split this mapping up into several different pieces, and once every n headers, like n is 2048 or 4096. And so we have blocks from 1 to 2048 all in one of these mappings, and after we've passed that block on the light client, we just generate that mapping locally and throw out all those headers. And we keep that mapping in a Merkle tree and keep the root of that. So that means that if we have any full node peer who has the same history as us, they can also generate that exact same Merkle tree and prove the header hash of any block in that history to us. And that allows us to keep, say, 2048 blocks, well, a reference to them in only 32 bytes. So if we ever want to get those historical blocks, we can do so securely, but we don't have to keep them ourselves. And warp sync is really important because light clients are a lot faster because they don't have to do this heavy operation of executing the transactions and regenerating the next state tree. To apply those updates is actually very heavy. It's really the bottleneck for full nodes right now. But even so, initial sync can be fairly slow. If you start at the genesis and you verify the proof of work for 5 million headers, it's going to take ages. So we have to think about other ways to sync. So warp sync is this idea that you can jump directly to the head of the chain with some level of security. So on proof of work, this is possible with thin client security. So at the very beginning, we just sort of get a trusted header hash and start from there. So we can't actually validate anything about this header hash. But then once we've downloaded the ancestry leading up to that, and we can do that in the background, we have a much higher security level, which would be equivalent to a typical light client security level. After this EIP 96, which makes some changes to how historical block hashes are stored in the state, we should be able to do proof of work warp sync, as well as under proof of stake systems or proof of authority systems to do a warp sync with full light client security from the very beginning. And that ancient block download can then be done on the background, potentially only on Wi-Fi. And I would say a fast and secure warp sync, or just the ability to get to the head of the chain quickly, is really crucial for introducing a micropayments-based scheme, because you can't actually enter into any kind of state channel contract unless you're already at the head of the chain, which means that full node peers would have to serve those blocks, those block headers necessary to synchronize for free while serving other requests for a cost. And that's a strange balance in the model because it opens up servers to spam very easily. So one final distinction I would like to make is that secure warp sync is different from having a hard-coded header hash or something equivalent to that in the client. So one thing you can do in a client is just say, when you make a release, we hard-code the latest hash of the chain. We say, OK, light clients, pick up from here. And that requires an additional level of trust in the developer, as opposed to a trustless warp sync where we're relying on cryptographic properties. So to speak about micropayments a bit, this is essentially the scheme that we have. So a light client and server open a state channel between each other. The client pays the server for every bit of data, and that can only really be done at the head of the chain. Because until you trust those headers at the head of the chain, you can't interact with any smart contracts there reliably. So our idea for how people can use this light client is actually very flexible because we've written it in Rust. And Rust is very flexible in terms of where we can compile and deploy it to. So right now we're building the light client for Android and iOS. It can be embedded in mobile apps. But one thing we're actually thinking of is to take the light client and compile it down to WebAssembly, and then embed that in a Chrome extension, which can give a Web3 JS instance to any web pages. So you would actually have a light Ethereum node that gives you really good security guarantees just running in your browser, easy as installing a Chrome extension. So we've begun work on compiling the light client to WebAssembly. It's fairly difficult because it's a very restrictive platform that doesn't have much in terms of the standard library APIs or what have you that exist already. So we would need some glue there on the JS side. But it actually is possible, and Rust is very well suited to that because it's such a low-level language. One of the hardest problems, I would say, for DApp developers using the light client is how we can search those historical logs. So I would say a lot of DApps make requests to a node that look something like, give me all the token transfers from the genesis up until now for this account. And that requires searching all these log events from the very beginning. That's really slow already on a full node, but on a light client, it is really slow. The reason is because we have to fetch all these headers and scan. There's a bloom filter in each header, and we have to scan those bloom filters. And the problem with these bloom filters is that they're limited to 2048 bits, and they're getting more and more full because they don't scale with the gas limit. So you have more transactions, more events, but the bloom filters don't get any bigger, which means the false positive rate goes higher. So you end up getting more and more false positives with each passing day that you download headers and you accidentally download receipts that are actually useless to you. So I'll talk about a few different ways that log searching can be done. So the standard way is basically just download the blooms for, say, block A, B, C, and D, or rather you download the whole header and the bloom is contained therein. And let's say we want to find a bloom filter where bits 2 and 5 are set. So we can just check all of those individually. So this first one matches, this first one doesn't match, the second one does match this filter, the third one does match, and the fourth one doesn't. But you can imagine if you had to do that 5 million times that it could be quite slow. Another approach is to do something that I would call horizontalization, which is for splitting up blocks into batches and then generating a bit vector, or rather 2048-bit vectors, each with the length of how large that group of blocks is. So let's say we're doing it with 4 blocks, and we have 8 bits in this sort of little bloom filter that I'm talking about, but in practice that's 2048. And the entries of these bit vectors are just whether that corresponding bit was set in the bloom of the corresponding block. So we've horizontalized, and now we would check for bits 2 and bit 5. And we can just download those bit vectors, so they look a little bit more like this, and we can check those without downloading quite as much data. The problem is, this doesn't work that well when the blooms are full because we still have false positive rates. It requires a fair amount of overhead on the full nodes to generate or store those historic horizontalized filters because they have to keep them for the historic blocks. And it requires an overhead on light clients to track the hashes or some other kind of reference to those horizontalized filters. So it's not a perfect solution, but it can be an improvement. I'd also like to talk a bit about light clients' role in sharding. So sharding is very hotly anticipated in the Ethereum community. We want to scale, we want to get more transactions. So light clients are actually crucial to that because it's not really possible to be a full node on every shard. There may be some super nodes, but on average, you would just be following 1 or 2 shards and being a light client on others so that you can check that certain receipts or transactions have been produced on other shards that are then coming over to yours, but you don't actually verify absolutely everything there. How are we doing on time? Good? I'd also like to talk a bit about Casper FFG because this is an upcoming improvement to Ethereum's scalability solution. It's like the first step in the Casper roadmap. So Casper FFG gives us finality, so the ability to see whether block hashes have been finalized and won't be reverted. The problem with Casper FFG as it stands is that this justification information about how the validators have voted on specific block hashes is stored in a smart contract. And light clients don't have access to that data easily. So they can't follow this full fork choice protocol of first following the highest justified chain based on the Casper FFG, and then following total difficulty. So it's a bit of a struggle to think of how light clients can fit in with this. Probably they'll just tend to follow the total difficulty-based chain and assume that the justifications will follow that. Or they could have peers send them like compact justification proofs of certain checkpoints in the Casper FFG system. But one thing that light clients can do is fairly easily follow dynamic validator sets under Casper. So again, the light clients can't read the validator set from the contract each block because they don't store the state. So they would, if you have to, every single block, make a contract call to read what the next Casper FFG validator set is, that's fairly difficult. Like, that's a lot of overhead for syncing. But they can still follow chains with dynamic validator sets if changes are only applied on finality. So this is something that's actually like the light client model can already support. So if we have a handoff proof from one validator set to the next, in essence that the previous validator set says this is going to be the next validator set, and then they finalize the block where that statement is made, then a light client can get, just have that whole thing sent to them. So they can see, okay, this block, that statement was made about the next validator set, and then this block is finalized by that previous validator set. So now I know that the set has switched to the next one. There is a slight caveat there if you use that to do an efficient warp sync, where you can just jump to the head of the chain, which is that you can have a prior validator set once they're no longer staked to just stop, they don't have any incentive to keep behaving correctly, so they could sort of just make stuff that was in a really ancient block and just sort of fork off from there and fool you. So that's a little bit of a slight security compromise, but if that doesn't work for your security model, you can always just sync the whole chain. And this is actually especially crucial. This dynamic sets approach is really crucial in a pure proof-of-stake chain where validators sign blocks. So right now, it's possible just to follow that total difficulty from mining, but when the block verification itself involves checking signatures on a block and not doing proof-of-work verification, we need light clients to be able to follow that. So just to give a little diagram of that whole thing, you can see first we have a block all the way on the very left, and that's under validator set A. So we say everything before this green line is under validator set A, and the next one is under validator set B. And the first block, we have a signal to the change to be created, and the light client can read that it may be through a log event or something similar. And then a few blocks later, that change is finalized. So any blocks building on that, the light client can then see should be validated under the assumption that validator set B is working on them. So to speak a bit to the developers in the audience, when you build an app on the light client, just what are some pitfalls you can avoid? So the first one, of course, is this ETH get logs. So it's fine when you're watching the head of the chain, especially if you're doing it in a publish-subscribe way, that, okay, a new block comes in, we check a Bloom filter, then we get the receipts if it matches, et cetera. But if you're going to history, it doesn't really work. So we have a few approaches, which I talked about before. One is to search locally. The other is to search locally with the stored metadata with that horizontalized filters. And the third approach is to have peers search, which, again, we can't always validate because we don't know if peers excluded something. So there's a few trade-offs there, but the fact is none of them are really going to be super fast. Another thing is getting anything by a hash, because hashes don't really leak any information about the block number where any changes occurred. So if you want to get a block by hash, and we have a situation where not everybody stores all blocks, then it doesn't give the light client any information about who they should ask for that data. Likewise, if you're trying to request state data at that block, or transactions or receipts. For example, if you want to get a transaction by hash, and it's an ancient transaction like it happened ages ago, that requires full node peers to store an expensive index of all hashes to the block hash and index where they occurred. And that's already around 2 gigabytes now, I think. For recent transactions, it's usually fine because they'll have them cached, but if you're looking in the history, it just doesn't, it can't be done quickly. And the last thing is estimation of gas. So that's crucial when you're trying to make a call to a contract that you know how much gas it's going to use. But the problem is, because Ethereum smart contracts are Turing complete, we can't predict that beforehand. So it also can vary from block to block because it can be based on how the state has changed in the meantime. So when we're estimating gas, we'll first start with a high upper limit and then a low lower limit, and we'll sort of binary chop to get in the middle. But another annoying thing is that smart contracts can actually see how much gas is remaining and branch on that. So it adds another level of inconsistency to actually the ability to reliably estimate gas. So it should be used sparingly because it can cause a very high overhead on the node, especially if the contract branches in case of different amounts of gas being remaining. For example, if you do your first estimation and then you realize, oh, we can probably go a little bit lower, and you do a second estimation, but the same state proof isn't sufficient for that second estimation with lower gas, you would have to then go to a full node peer and get another state proof, and that's fairly heavy. So I think it's interesting to think about how the light client might fit into the broader ecosystem. So light clients can work on mobile devices. And Whisper, for example, makes a really powerful tool for messaging between peers in a decentralized, anonymous, and private way. And it actually works pretty well for, say, medium latency state channels, not where you have thousands of transactions per second, but maybe where you have one every 10 seconds or anything slower than that. And for example, there's a project called Status, which is already showing how that can be used, that you can have a mobile app that's running a light client and running Whisper for chat, for state channels, for applications. So as far as our roadmap goes for the Parity Light client, you can actually use it today. So you can run Parity with the --light flag in beta releases, and it'll start to sync the chain. If it starts from the Genesis, don't worry. It might take a while because it has to get all those headers. We've already got a pull request open for that essentially hard-coded header hash if you trust that. It is opt-out. So that would get you to the head of the chain very quickly if you trust that hard-coded header hash that's in the client. The UI is still being rebuilt around light client best practices because it takes a lot of effort as a developer to think about what kind of load you're imposing on the local node. And if you're running a full node, you've got everything locally and you don't have those same performance implications. But when you're writing a UI-based Ethereum app around a light client, you have to be very careful about that. And we're also starting the work to compile down to WebAssembly, where you can embed a light client in your browser. So if you're interested in following the progress, all the code is open source. We've got that in the main Parity Ethereum repository. You can follow that at this GitHub link, paritytech/parity. And we encourage you to check it out or even contribute. If you have any questions, now would be the time. Yes?
Can you say what are the main differences between the Parity Light client version and the Go Light client version?
Yeah, so the protocols are different, primarily because of this round-trip based stuff that I was talking about before. So what Go LES allows you to do is have multiple requests of the same kind in a single packet, but not multiple requests of different kinds, where the later ones reference outputs of the priors. The other main difference is with this canonical hash tree stuff. So Go has a canonical hash tree that's generated for all blocks up until now, but now is changing periodically, whereas Parity Ethereum is doing that with smaller canonical hash trees that the light client can generate locally. So it can stay up to date without having to get any trusted information from the developers or other full nodes. Anything else? Well, thank you very much.